Let little f be a continuous, real-valued function defined on a closed interval from a to b. Furthermore, let big F be the function defined for all x by big F is the integral from a to x of little f of t dt. Then, big F is continuous on AB, it's differentiable on AB, and furthermore, the derivative of big F is little f. Now, what FTOC Part 1 does is it combines both the integral and the derivative. It tells us that they are opposites. That if you go in the derivative direction, you're going down the ladder, but then the integral direction, you're going up the ladder. So this is a major theorem in calculus right here. Let's begin breaking this down little by little. We have the integral from some constant a, and it could be any constant. It could be 0, it could be 5, it could be 100, it could be -5, up to our variable x. And our function inside is in terms not of x, but it's in terms of t. This is extremely important. Now, what it says here is that if you take the derivative of big F, you end up with little f. Or in other words, the derivative and the integral kind of cancel out to just give you that nougaty center inside of the integrand. In other words, if you were to take the derivative of big F of x, this is the same thing as taking the derivative of the integral from a to x of little f of t dt. And as we know from part 2 of the fundamental theorem, we need to have a antiderivative of little f of t. Well, if we go backwards in this theorem, which we should never do, but for the sake of argument, let's do it. If we go backwards, the derivative of big F is little f. Well, what that means, by definition, is that big F is the antiderivative of little f. It's one up the ladder of derivatives from little f. So we can use big F as the antiderivative of little f. So this is the derivative of big F of x minus big F of a. And this right here is using the fundamental theorem of the calculus, part 2. Now, the derivative of big F of x, we already said that the derivative of big F of x is little f of x. And the derivative of negative f of a, well, a is a constant. And when you plug any number into a function, you're getting just another number. And the derivative of some number is just 0. And so, what we've noticed here is that the derivative of big F of x is equal to little f of x. Now, what happens when you flip your limits of integration? What would happen if you were taking f of x is equal to the integral from x to a of f of t dt? Well, then when you took the derivative of this would be the derivative of the integral from x to a. This is the derivative of the left-hand side as well, of f of t dt. And if you use FTOC part 2, this is the derivative of big F of a minus big F of x. And of course, the derivative of big F of a, which is a constant, is just 0, minus the derivative of big F of x is a little f of x. And so you just have a negative in front of your functions, just negative f of x. And the reason for this is because when you flip your limits of integration, you always put a negative out in front. So this does make perfect sense. Problems using FTOC Part 1 are ridiculously easy. Check it out. If big F of x is equal to the integral from -2 to x of e to the t sine of 3t dt, find the derivative of big F. Well, alright, we have our constant in our lower limit, we have our variable in our upper limit. That's all set to go. And that's all we need to be able to do this. So what's going to happen is the derivative of the integral cancels out, and instead of t, I'm going to replace that with x. And that's all you have to do on these problems. So f prime of x is equal to e to the x sine of 3x. Done. Let's see what happens theoretically to the fundamental theorem of calculus part 1 when we throw chain rule into the mix. So consider y is equal to the antiderivative of a to some function u of x. We have seen this before as stuff, and this is of some function f of t dt. Then if we wanted to find the derivative of y, we would have to find the derivative with respect to x of the integral from a to some function of x, aka stuff, of f of t dt. Now using FTOC part 2, we can rewrite this as the derivative with respect to x of the antiderivative of little f of the function u of x, our stuff, because we're plugging this is our b, we're plugging it into big F, minus big F of a. Well, at this point, we notice that we're going to have to use some chain rule because we have big F of stuff, some function of x. And when we take the derivative of big F of stuff, we take the derivative of our outside function f, which is little f, we plug in the stuff, we keep it in there, and then we multiply by the derivative of the stuff. So that's u prime of x. And of course the derivative of some constant, since a is a constant, plugging any constant into a function is still a constant. So the derivative of a constant is just 0, so that goes away. And so when we use some function of x, some stuff, in my upper limit, then we have to use chain rule. And what we do is we plug u of x into our function and then multiply by the derivative of u. We're going to let y equal the integral from -1 to x squared of cosine of t dt. Let's find the derivative of y, or in other terms, y prime. Well, that requires us that the derivative of the integral from -1 to x squared of cosine t dt. Our constant is in the lower limit, that's good. However, our variable isn't just x. Now it's x squared, which means we have to do one more thing on top of everything else. Not only do we plug in this entire thing into cosine of t, but also we multiply by the derivative of x squared. You have to use chain rule here. So, here's what you do. First, you plug it in. Cosine of x squared. And then you multiply by the derivative of your stuff. The stuff up here, which the derivative of x squared is 2x. So the answer is 2x cosine of x squared. Let's try one more. What if you took y equals the integral from 5 to cosine of x of secant squared t dt? Well, y prime, you would plug cosine x into t, so we have secant squared of cosine x times the derivative of cosine x, which is negative sine x. And so the answer is negative sine x times secant squared of cosine of x. And that is using FTOC Part 1 with chain rule.
Okay, in this video I want to show you how to combine the fundamental theorem of calculus and the chain rule to get some pretty strong results. You sometimes get problems like compute the derivative of the integral from 3x to x squared of e to the minus s squared ds. And at first glance this looks horrible. How are you ever supposed to find that integral? And then once you find that integral, how are you supposed to take its derivative? In fact, we know that the integral does make sense. We know that there is an antiderivative of e to the minus s squared. We just don't know the formula for it. So let's let f of x be the antiderivative of little f of x, which is e to the minus x squared. So we are trying to take the derivative of the integral from 3x to x squared of f of s ds. And that's the derivative. Well, we use the second fundamental theorem of calculus and say to do this integral from 3x to x squared, we just take big F of x squared minus big F of 3x. Now, we don't happen to know a formula for big F, but that's okay, because now we apply the chain rule. The way you take the derivative of big F of x squared is you take f prime of x squared times the derivative of x squared. And the derivative of big F of 3x is f prime of 3x times 3. And now here comes the magic. Big F is an antiderivative, so the derivative of big F is little f. So you just plug it in. And since f of x is e to the minus x squared, this gives you e to the minus x to the fourth times 2x minus e to the minus 9x squared times 3. And there's your answer. In general, if you're ever given problems that look like find the derivative of the integral from, let's call it g of x to h of x of f of s ds, you say, oh, that's the derivative of big F of h of x minus big F of g of x. And you don't worry about the fact that you don't know a formula for big F, because you're going to take his derivative, and you do have a formula for the derivative of big F. It's little f. So this is always going to give you f prime of h of x times h prime of x minus f prime of g of x times g prime of x. And that's going to be f of h of x times h prime of x minus little f of g of x times g prime of x. So you often run into these kinds of problems, and by combining the chain rule with the second fundamental theorem of calculus, we're not actually using the first fundamental theorem, we're using the second fundamental theorem, we get the answer. In fact, this is a backdoor way of seeing why the first fundamental theorem is true. If you believe that every function has an antiderivative, and for that you really do need to go through the proof of the first fundamental theorem, but if you believe that antiderivatives exist, then the derivative of the integral from a to x of f of s ds, well, that's the derivative of big F of x minus big F of a. The second fundamental theorem of calculus says you find an antiderivative and you plug in at the endpoints, and that's how you do an integral from one spot to another spot. And that's f prime of x minus 0, because this is a constant, doesn't depend on x, so its derivative is 0. And that's little f of x. So that's another way of understanding the first fundamental theorem of calculus. Once you have the second fundamental theorem of calculus, the first fundamental theorem of calculus comes almost for free.